Okay, so today we're going to discuss the substantial derivative, and this is again in chapter 5. Okay, and the substantial derivative is sometimes called the total time derivative. The material derivative, the Lagrangian derivative, and a few other names. Okay, and so here, what we're going to, what this derivative gives us is that this gives us, if we have fluid flowing in a velocity field, like this, and we have some streamlines that look like this, and we have a fluid particle here, what is the acceleration acting on the fluid particle? Okay, and so we use the substantial derivative to do that. And so so it's y, x. Okay, so we use this as substantial derivative to do that, but recall that the velocity vector is given by u I hat plus v j hat plus w k hat in Cartesian coordinates. Okay, and in general, u is a function of space and time. V is a function of space and time. And w, which is the z component of the velocity, is also equal to a function of space and time. Right, so if I scroll up back to this picture here, we have, at this point here, we have a different velocity vector than, say, at this point over here. And if the flow is unsteady, that means these velocity vectors here are changing as a function of time. And so we need to account for that. And so, now given this, what is the acceleration of the element, or the fluid particle, as it travels in space and time? Okay. And so here we have the velocity of the particle, or of a fluid particle, is equal to the velocity vector at x, y, z, and t. Okay, and so we're assuming that the particle instantly accelerates to the fluid velocity. Right? So that means that the velocity of our fluid particle, that's just moving along with the fluid, is just equal to the fluid velocity. Okay? But this fluid particle is moving around at the function of time. So it could be moving like this. So this is the t equals t naught, and it's going to be moving as a function of time. And we're going to have t equals t1 here. So its position is changing as a function of time in the velocity field. So x, y, and z for the particle are functions of time. Due to the position of the element changing. Okay, so the velocity of the particle is more properly written as v x of t, y of t, z of t, and time itself. Okay? And of course, this time here accounts for the location of the particle at time t. Okay? So now we want to find the acceleration. Well, the acceleration of the particle equals dv of the particle with respect to time. But here we have a function, but this is not just equal to dv particle dt. And the reason being that this is not just equal to the time derivative of the particle velocity is that x, y, and z are also functions of time. So we need to use the chain rule. So need to use the chain rule. Okay, and so recall for the chain rule, if you have some function f, that's a function of q, which is a function of time, and a function of time, then df dt equals partial f partial t plus partial f partial q dq dt. Okay? So we're going to use this chain rule right here on the acceleration of the particle. Okay? So dv, so the acceleration equals dv of the particle with respect to time, and we need to use the chain rule on this. So this would be partial v, partial t, plus the derivative of the derivative of x with respect to time, so dx dt times partial v partial x plus the similar term for the y derivative. So we have dy dt partial v partial y plus dz dt partial v partial z. Okay. And so this looks like we've expanded it into a bit of a mess, but notice that dx dt by definition is just the fluid velocity, or dx dt is the x component of the fluid velocity. dy dt by definition is the y component of the fluid velocity, and dz dt by definition is just the z component of the fluid velocity. So the acceleration equals partial v partial t, which is the time derivative component of that, plus u, partial v, partial x, plus v, partial y, plus w, partial v, partial z. Okay? And so this is the acceleration of the particle as it travels through space in time in the fluid velocity field. Okay, and so this here is a very common operator, and this is more commonly written as the acceleration equals cap dv cap dt, okay, where this cap dt, this is an operator, and it can act on a lot of variables, not just the velocity, and this operator is defined as partial t plus u partial x plus v partial y plus w partial z. And so these empty things here are stand-in for any quantity. Okay. So this here is called the substantial derivative. Okay. And if you use v for the substantial derivative, you get the acceleration as we have here. But the substantial derivative is applicable to many other things. So for instance, if you want to find the time rate change of any quantity on the fluid particle, you simply use the substantial derivative acting on that property. So if you want to find the time rate change of density, which would be d rho dt. Okay, and so again, here we have a fluid particle. It's moving in a vector field of the fluid, and we want to find at this point here what is d rho dt for the particle, right? Because it could be compressing, the temperature could be changing, all kinds of things. Well, if we want to find the total time rate change of density of the fluid particle, we use the substantial derivative for that. And so we just apply this formula up here, but in these empty spaces here, we just put in density. So this equals partial rho, partial t, plus the x component of the velocity vector, partial rho, partial x, plus the y component of the velocity field, partial rho, partial y, plus the z component of the velocity field, partial rho, partial z. Okay, so if you know the density at a position as a function of position and the fluid velocity, you can also find the total time rate change of the density field. Okay, and so and this formula here is valid for 3D Cartesian coordinates. Okay, so what about other coordinate fields? Well, in general, in vector form, d dt equals partial t plus v dot grad of that operator. Okay, and so this is general vector form. Okay, and if you actually need to use something other than the 3D Cartesian coordinates, you could look up what this operator is in various coordinate systems. Okay, and so as an example, we're going to go through an example now of how you can use the substantial derivative to compute the acceleration at a given point. And so here, example, oops. Okay, and so we have the flow given over a sphere. This is actually called creeping flow. And we have a fluid velocity field given like this. And at the very center streamline, this is point A and this is point B. What we find, a streamline, we find that at the center streamline, the velocity field for that is given by u, which is a function of x. Oops, that's a really bad u. I hat, and this equals some v naught times 1 plus the quantity a cubed over x cubed I hat, where a is the radius of the sphere. Okay, and so what we want to find is the acceleration of a fluid particle as it travels from A to B. Okay, so find the acceleration of the fluid particle as it travels from A to B. So the solution so we're given a velocity field, and the acceleration is equal to dv dt. This equals partial v partial t plus u partial v partial x plus v partial y plus w partial v partial z. Well, v equals v naught times the quantity 1 plus a cubed over x cubed I hat. Okay, And so plus 0 j hat plus 0 k hat. So this implies that v equals 0 and w equals 0. And also, v is not a function of time, so this is a steady velocity field. So v is not equal to a function of time. Okay? So the acceleration then equals u partial v partial x. So this equals, so u is this component over here. So this equals v naught times 1 plus a cubed over x cubed times partial x of v, which is v naught times 1 plus a cubed over x cubed I hat. Okay? So if we substitute everything in and do this derivative over here, this winds up being v naught times 1 plus a cubed over x cubed times v naught times a cubed times minus 3 x to the minus 4 I hat. Or the acceleration equals minus 3 v naught squared over a times the quantity 1 plus a over x cubed over x over a to the 4th I hat. Okay, and so that's how we can use the substantial derivative to find the acceleration of the fluid of the fluid. And note that even though there's no explicit time dependence on this velocity vector here, so it's steady, there's still acceleration of the fluid due to these terms here. Okay, and so in general, dv or d dt equals partial t plus u partial x plus v partial y plus w partial z. This here is called if acting on v, this is the local acceleration of it's for the particle. Okay, and this is also called the unsteady term. Okay, and this group of terms here are called the spatial derivatives are sometimes called the convective derivative, because this accounts for the motion of the particle as it travels through a velocity field. Okay, and so this term here accounts for the unsteadiness, and this term here accounts for the through the convective effects as the fluid particle moves from, say, point A to point B in the velocity field. Okay, and so you can use the substantial derivative on more than just the velocity to find the acceleration. And now this operator here looks very formidable, but if it's acting on a variable such as temperature or density, the substantial derivative moves quantities in space and time. Okay, so all this crazy substantial derivative operator does is it just moves things around. Okay, with the exception of v for the acceleration. But say we have our little a fluid domain here, x and y, and we have a high temperature bubble here. So we have low T outside, and we have high T inside, and the velocity field is perfectly uniform v equals 1 I hat plus 1 j hat. So basically, the fluid velocity field is just moving up at a 45-degree angle. Okay? And so, intuitively, if we have this high temperature bubble here, and it's in a perfectly uniform flow field, what is going to happen to this high temperature bubble as time progresses? Well, you could imagine if we had a solid particle that had a different temperature than the surroundings, and it was moving up at a 45-degree angle, it would just simply move in this 45-degree angle until time t2, and this particle will just simply move up and to the right with the flow field. Okay, so this is the particle at time t is greater than t naught. Okay, and so all this did was this took this high temperature blob, and if we just called it a particle, and we move that particle upwards, with this velocity field here, this fluid particle will just move up and to the right at a 45-degree angle. Now, if instead of considering this as a solid particle, instead it was just a blob of fluid, it would still move at this exact 45-degree angle, and what the substantial derivative does is, if we apply this temperature, we have dt equals partial temperature, partial time, plus u, partial t, partial x, plus v, partial t, partial y, plus w, partial t, partial z. Well, w is equal to 0 here. So all this operator does is this simply moves the high temperature bubble up and to the right. right? So this crazy substantial derivative operator, it just simply moves things around. It does nothing more than that. Okay? So how else is a substantial derivative useful? So let's consider conservation of mass. So, we got this, why even spend our time going over this? I mean, we can use it to find acceleration of velocity fields, but it's also very useful to look at the governing equations. So let's examine conservation of mass. Okay, so recall that conservation of mass in 3D Cartesian coordinates would be partial rho, partial t, plus partial rho u, partial x, plus partial rho v, partial y, plus partial rho w, partial z, is equal to 0. So now, let's use the product rule. On these terms. Okay, and so here we're implicitly assuming a differentiable flow field. Okay, so basically we are assuming that the product of rho u, the product of rho v, and the product of rho w are smooth and differentiable. That is not always the case. This is not true if you have shock waves. Okay, so a lot of us who work with compressible flows, we cannot use the product rule here because we have non-differentiable quantities. But here we're just going to assume that the flow field is smooth and we can safely use the product rule here. Okay, so I'm going to expand everything out. This is going to look like it's going to be a huge mess at first. So we have partial rho, partial t, plus u, partial rho, partial x, plus rho, partial u, partial x, plus the product rule on the y derivative term, that's v, partial rho, partial y, plus rho, partial v, partial y, plus the product rule on the z derivative term here, so that's w, partial rho, partial z, plus rho, partial w, partial z, and this whole thing is equal to 0. Well, I'm going to group some terms here. So this equals partial rho, partial t, plus u, partial rho, partial x, plus v, partial rho, partial y, plus w, partial rho, partial z, plus the density, these terms here, and they're all multiplied by the same density, the density times partial u, partial x, plus partial v, partial y, plus partial w, partial z, and this is equal to 0. Notice here, I'm going to scroll up a little bit. Oops, I won't, I guess it's too far up. This here is just d rho dt. Okay. And this term here is the divergence of the velocity field. Because if you recall, I showed this earlier, the divergence of the velocity in 3D Cartesian is partial u, partial x, plus partial v partial y plus partial w partial z. So this equation here, if we use the product rule on partial rho u partial x, partial rho v partial y, and partial rho w partial z, this turns into d rho dt plus rho times the divergence of the velocity is equal to 0, or 1 over rho d rho dt equals minus the divergence of the velocity field. So what's important about this? Well, what if the flow is incompressible? Well, if the flow is incompressible, one condition, one way to have an incompressible flow is rho equals a constant. Okay? And if rho equals a constant, then d rho dt is equal to 0. Right? Because partial of rho with respect to time x, y, and z will all be 0. So that means the substantial derivative of density with respect to time will also be 0. So if d rho dt equals 0, then the conservation of mass up here simply becomes 0 equals minus the divergence of the velocity field, or the divergence of the velocity equals 0, and that's valid for incompressible flow. Okay, and so this here is continuity for incompressible flow. Okay, and also, and this is entirely consistent with our RTT. And so if we use from RTT, where if we assume the density was constant, we had partial t, the integral of the curved line of rho dv, plus the surface integral of rho v dot n hat dA is equal to 0. Well, that's equal to 0 because density is constant, and we can cross that out. So this implies that the surface integral of v dot n hat dA is equal to 0. Well, we can use the Gauss divergence theorem on this, and this becomes the volume integral of the divergence of this vector here, v dv. So if we apply this, we have the volume integral of the divergence of the velocity dv is equal to 0. So, and as we argued with the conservation of mass for a general fluid, the integrand must be 0. So this implies that the divergence of the velocity field is equal to 0. So this is entirely consistent with what we used as an incompressible flow when we worked with continuity earlier. Okay, so this is completely consistent with that. Now, what this shows, though, is that it's not necessarily that we need constant density to have an incompressible flow. Instead, we just need the substantial derivative of the density with respect to time to be equal to 0. Okay, and so the true condition for incompressibility is just simply that the velocity field is divergence free. Okay. And again, this here is valid for incompressible